Welcome back. In this lecture, as you can see, that I'm going to talk about the Higgs physics and how effective field theory or effective standard model effective field operators can contribute to some of these observables related to Higgs physics. That's what I'm going to talk about. And once again, there are many possibilities that one can talk on. And however, I will restrict myself to a couple of examples, and we will see how these things are interesting in the present context of the searches that are going on for the Higgs physics. Okay, so it's customary to remind ourselves that we already have talked about many times, but it's once again still helpful to remind ourselves that the standard model gauge group SU3C cross SU2L cross U1Y via spontaneous symmetry breaking by a suitable choice of the Higgs doublet with a hypercharge of y equal to half breaks the gauge group into a remnant SU3C cross U1 electromagnetic, and which generates basically the standard model fermion masses and gives rise to massive weak gauge bosons W plus minus and Z. And you remember, this is the Lagrangian that we talked about, which includes the scalar potential involving this guy in a gauge invariant way. The parent symmetry is still SU3C cross SU2L cross U1Y. Well, by the way, SU3C doesn't work too much here because it is only transforming under this SU2L cross U1Y. And once you choose this mu square in the scalar potential less than 0 and then identify the minima associated with the scalar potential, it shows infinitely many degenerate minima, and once you choose a specific one that breaks SU2L cross U1Y symmetry, and one specific choice of this vacuum is like this, where you assign the Webb to this guy phi 3 by V plus Hx, where this is the fluctuation about the vacuum and which is the Higgs boson, and the other massless fields become the Nambu-Goldstone bosons, and they are sort of responsible for giving masses to this W and Z bosons. And then we also have the Yukawa interactions, which once you put the vacuum expectation value to this phi field here will generate the electron masses. For this term, you generate the down type quark masses. Via this interaction, you generate the up type quark masses. And in the standard model, we do not add the right-handed neutrinos, but that story we have already talked about. Okay, but the question that we are asking is that how do we know what kind of Higgs that we are actually looking for? So, the subsequent slides that I am going to talk on is essentially devoting that same idea or the same question, that the Higgs that we have discovered is what kind of Higgs it is, and how the presence of effective operators beyond dimension 4 can help in illuminating that thing. So, once again, let me sort of remind you that within the standard model Higgs, these are the interactions with the gauge bosons which stems from this kinetic term, and the Higgs interactions with the fermions get generated from the Yukawa interaction, and these vertices are proportional to the fermion masses. These are the proportional to corresponding gauge boson masses. And then there are self interactions, and which are from the scalar potential itself, and there is a trilinear Higgs interaction, and this is a very crucial one because this is ideally not there in the scalar potential, but once you write phi equal to V plus H and expand this potential, then you actually generate this trilinear term. So, this is very important to probe in order to know the symmetry breaking mechanism that actually is there. And in a generic sense, you can say that measurement of all these couplings and the parameters associated with the scalar potential will actually be able to confirm the nature of the Higgs. And here the effective field theory comes in and asks us, gives rise to some kind of questions that helps or in a sense affect our observational consequences, and that is what we are going to talk about. And there is a video before we proceed further which I want to just show. So this is from CERN, and this is actually about the discovery of the Higgs boson, which I just wanted to show you. I mean, not always. It's the CERN buses flying actually, Jose. So this is the LHC.
Today is also a special day because we hear two presentations from the two experiments, Atlas and CMS, on their update on a search for a certain particle.
I will give the status of the CMS Higgs search. The standard model is here, is shown here. This is what we know. These are the particles making up the standard model that we've known and seen up till now. But there's one piece that's missing, and that's what we call the Higgs. It's very interesting. It's pretty much in agreement with the standard model at 95% confidence level. Standard model's here, this is what we're measuring. So it's a bit off, but again, we need more data. We've seen this, we calculate this, and we conclude by saying that we have observed a new boson with a mass of 125.3 plus or minus 0.6 GeV at 4.9 standard deviations. Thank you.
Atlas is very pleased to present here today updated results on standard model Higgs searches based on up to 10.7 inverse femtobarn of data recorded in 2011 and 2012. And it's a big honor and a big emotion for me to represent this fantastic collaboration at this occasion. So, quantification of the excess. This slide shows, again, the usual p-value as a function of mass, and also the significance now as a function of mass. This distribution is extremely clean, except one big spike here, in this region here. So, zooming in this region.
You know the name of this person, right?
Well, I would like to add my congratulations to everybody involved in this tremendous achievement. For me, it's really an incredible thing that it's happened in my lifetime. It's taken...
Yeah, I think we can go ahead now. Okay, let me bring me back my slides. Where is it? Yeah. No. Once again it started. No more. Sorry. Yeah. Okay, all right. So, yeah, that was a fantastic discovery of Higgs, and yeah, it's once again interesting to note what are the Higgs production channels at the LHC, and this is what is called vector boson fusion. Quarks exchanging W or Z, producing Higgs with two jets, and this channel is what is called the gluon fusion channel. and this is what is called the Higgs-Stralholm process, because you are producing an Higgs in association with a W and Z, and then there is a Higgs with a Z via this gluon fusion. There is a production mechanism with top pair, and this is also an interesting channel where you actually produce Higgs in association with a single top, and that's also very interesting. At the collider, when you look into the results that people have obtained so far, for these different channels that we just talked about, they provide you with some term called mu, and this parameterizes basically sigma times the branching ratio of the observation divided by sigma times the branching ratio in the standard model. What it means that if this mu value is observed at 1, that means your observation is very consistent with standard model. If not, then there is a possibility of saying that what we are seeing has maybe something more than what the standard model offers. So you can see this list, and this is for 13 TeV with 138 femtobarn inverse from one of these detectors called CMS. You showed that there are two detectors which were searching for Higgs. One is called the CMS and the other is Atlas. So both confirm the signal of Higgs, but this was showing that there is some deviation in the ZH channel and WH channel, little bit of a discrepancy with vector boson fusion, but otherwise more or less consistent with mu equal to 1. Something similar happens in the Atlas case, and I think this is in the y-axis. You have the different production modes of the Higgs boson, and on the x-axis, basically these are the Higgs decay branchings that through which you probe these channels, like Higgs going to BB, WW star, tau tau, or ZZ star, etc. So in this way, you can see that mu equal to 1 is this line, and whatever the little deviations that you actually spot there is basically showing that the observations that have been made so far is not absolutely consistent with what standard model provides. So this gives you an opportunity to probe the possibility of new physics entering into the Higgs searches in some way for those cases which actually deviates from the standard model observation. Then there are also measurements of the Higgs couplings, and usually what the way that people parameterize it is once again via something called a kappa, which is essentially the ratio of G observed by GSM, where G observed is the coupling that you actually could extract, and the GSM is the coupling which is actually predicted from the standard model Higgs isodoublet. And once again, you can look into this list and find out the deviations. So in principle, if kappa is equal to 1, that basically means that you are pretty consistent with standard model, and once you deviate from that, that gives you an opportunity of probing the Higgs coupling beyond the standard model. The question is if there is something that contributes to that. So this is an exercise which people do. Now let me bring back to the list of operators which Jose introduced yesterday, the dimension 6 ones. Why dimension 6 ones? Because in the dimension 5 we have already seen that only couple, that modifies the Higgs neutrino coupling, and that doesn't affect our observations to a great extent. So in this dimension 6 operators, we have operators involving the, yes.
Sir, I have one question.
Yes.
Sir, my question is that is the wave, the 246 GeV, it's experimentally measured?
The wave cannot be measured, unfortunately, but
the mass is measured.
The consistency, yes, mass is measured.
But
and
coupling is also not directly measured, that lambda?
The trilinear coupling, yeah, the quartic coupling or whatever you say, that
yes.
I think that is vaguely measured. The lambda measurement is not that, in the kappa framework, I think lambda is not included. Yeah, because it's difficult at LHC to measure the trilinear because that lambda coupling will be best measured via this triple Higgs interaction, right? So that is difficult to measure at LHC.
Okay, then from where did this 246 experimentally came that it's the wave we are taking?
No, it's just a consistency between the MW and MZ because there is a relation of mz square equal to mw square cos square theta w.
If our rho equal to 1.
Right, rho equal to 1. So that actually essentially confirmed what is the value of the vacuum expectation value. So we couldn't measure the value of the vacuum expectation value, but the consistency relation between the measurement of Z mass and the W mass and their interrelation confirms what is the vacuum expectation value that the isodoublet should produce. Yeah.
Okay.
So it's not a direct measurement of the vacuum expectation value, if I understand correctly, right? The mass of the W or mass of the Z. Because we know also that the weak couplings are known.
Yes.
G and G prime. Because that gives you the measurement of tan theta W equal to G prime by G, right? And we know sine square theta W is 0.23. So that determines the G and G prime. And once you know those, you know MW is simply G into
Yes.
V.
V by yes.
GV by 2 or GV or something like that. Whatever.
Yes.
Yeah.
Any question? So are not all the intercoupling experimentally done? What does it mean for standard? All the intercoupling experimentally done?
Yeah. Well, this is what the picture actually shows. This kappa framework, which shows, okay, all right, we have measured the Yukawa couplings to a great order of precision, but not yet there to fully confirm that it is coming from the Higgs isodoublet, the one that we postulated.
That means it is not related to purely standard model?
Yeah, exactly. So that's the question that we are asking, that the Higgs that we have discovered, whether it's a pure standard model like Higgs or there lies any option to go beyond the standard model, including another singlet, give it a vacuum expectation value, put together. All these questions are open and you can constrain your observations from this kind of measurements. So those windows are not completely closed yet. That's what we can say. Okay, so let's proceed. So let me sort of come to this dimension 6 operators. So you have gauge field operators. You have the Yukawa modifiers, which will come from this kind of terms like psi square phi cube, and it's obvious that it will actually come from this kind of terms. Then you have dipole operators coming with this inclusion of sigma mu nu. You have the Higgs current operators, which has this phi tilde dagger d mu phi with up bar gamma mu dr, and it's same, you can do it with all the other doublets that are there, not only the left-handed doublets but also with the right-handed singlets. And then you have the bunch of 4 Fermi operators, and these are also classified like all these combinations which Jose discussed, that there are L bar L combinations, R bar R combinations. That means all the fermions that are introduced here to construct these operators are left-handed doublets. Here they are right-handed singlets, and in this case they are a combination of left-handed doublets and right-handed singlets. And then you can also have a tensor kind of operator here with a combination of L bar R bar L. And then there are some operators, the others are called the scalar operators of that kind. And then there are B violating operators also, which you can constitute. So now, before proceeding further, I would like to just give you a little insight about the CP symmetry and the fields. So we would like to find out the CP transformation of the field strength tensor. So what was the definition of the field strength tensor, which is actually B mu nu equal to del mu B nu minus del mu B mu. So this is something that we know. The parity of del 0 remains the same, where parity of del I takes a minus sign. Parity of B naught is once again the same, the parity of Bi is minus Bi. What about the charge conjugation? Charge conjugation of del mu is plus del mu, where the charge conjugation of B mu is minus B mu. Now here you would like to ask this question, that why the charge conjugation on B mu gives you a minus B mu. The answer to that is as follows, that when you do this charge conjugation operator on the psi bar gamma mu psi, then it actually picks up a negative sign. And if you want your B mu psi bar gamma mu psi to remain invariant under C, then the B mu has to pick up a sign under the charge conjugation. Now, you can use these results to actually find out the parity transformation on B00, which remains the same, Bij, which remains the same, B0y will pick up a negative sign, and Bi0 will also pick up a negative sign. In general, you can show that the parity acting on B mu nu will give you B mu nu. What about the CP transformations? Having P acting on B mu nu gives you B mu nu, you can say that Cp on B mu nu is essentially C acting on B mu nu, and following this result, you can say that the Cp acting on B mu nu will give you a minus B mu nu. What about the conjugate field strength tensor, which is B tilde mu nu? We know that it involves a Levi-Civita symbol, or antisymmetric tensor of rank 4, epsilon mu nu rho sigma B rho sigma. And this is something that you can verify, that the P on epsilon will actually have a minus sign, minus epsilon, where C on epsilon will remain the same. And if it is the case, then unlike the Cp transformation on B mu nu giving you a negative sign, here you can see that P acting on epsilon mu nu rho sigma will actually take another additional sign, and that will get cancelled when the C acts on this field strength tensor and changes its sign. So, B mu nu tilde remains invariant under Cp transformation. So, therefore, the question is that now you come to this question, that what happens to the Cp transformation on the Higgs doublet. The P of phi remains phi, C of phi gives you phi star. So, Cp acting on phi dagger phi essentially gives you phi dagger phi. Cp transformation of the operators which concerns us. Now, say for example, take this operator O phi b, which is like phi dagger phi B mu nu B mu nu. What will be the Cp transformation? Cp transformation acting on phi dagger phi, Cp transformation acting on B mu nu, Cp transformation on this guy, and you know that because the point is Cp on B mu nu will pick up a negative sign, and so here, so therefore there will be no change, and the Cp transformation on O phi b remains the same. What happens on O phi b tilde? Now the point is this operator constitutes of one field strength tensor and one conjugate field strength tensor. So the Cp transformation will have a sign here, no sign here, no sign here. So there will be a negative sign here. So therefore these operators will be Cp odd, like those which will involve B mu nu tilde. So this is the conclusion. So these operators, this kind of operators are Cp odd operators. Are these the only one which is Cp odd? The answer is no. These operators which involves the field strength tensor and its dual, and they are showing Cp violation as we just discussed. But on the other hand, this kind of operators, because they can involve complex Wilson coefficients, from that part you can induce imaginary parts in these operators, and they will also provide you Cp violation. So therefore these kind of operators are classified as CP-odd operators which will affect the Higgs physics. Now this is an interesting, so once again I am not going to remind you, so the coefficients are named essentially, so these are the Wilson coefficients which sits in front of all these dimension 6 operators. So what one can do, that one can go back and look up a particular process that interests you, like for example Higgs physics, and you see that these are the class of operators which will affect some observable or the other related to Higgs physics, and this I am actually copying from one of the paper of Maltoni et al. And similarly, you look for dye boson production, these operators will come into play. TT bar vector boson, this set of operators will come into play, and so on and so forth. Top, EW, etc. And some of this will contribute to electroic precision observables, TT bar production. So these are all relevant processes which LHC is now looking into, and this Wilson coefficients, that means those corresponding operators will actually contribute to this kind of observables. So let me get back to the Higgs coupling specifically. For example, I mean, let's think of the vector boson fusion process, ZZ Higgs. Now, it is not very difficult to kind of expand this operator like H dagger d mu H star, H dagger d mu H, and if you expand this, which has this coefficient named like CHDD, I mean my conventions have been different because I am copy pasting from different places, I apologize for that, but never mind, but you can show that this will actually give additional contributions to the ZZ Higgs coupling to the one which is existing. So therefore, the presence of this kind of dimension 6 operators will give you additional contribution to the ZZ Higgs coupling. And so if you have any ifs and buts in the measurements of Z Higgs coupling, you might think there is a contribution which is coming from this kind of dimension 6 operators. And this exercise can go on for other operators also, like H dagger H, G mu nu will produce an additional contribution to glue Higgs, etc. And this exercise can be extended for all these different operators involving the Higgs field that we have written. Yeah, so I am not repeating further, but you can see that this is the list and one can verify, for example, QQ2 TT bar. So there is an interesting part, this slide is important because suppose you want to produce TT bar Higgs at the LHC. So you may think that those operators are only contributing, those effective operators can additionally only contribute which has explicitly the Higgs in it. But the answer is no, because in that process you also have a graph where you can produce via ZTT bar, and this vertex ZTT bar that can get additional contribution from this vector current interaction operators. So that will give you additional contribution to finally TT bar H production also. So therefore, when you are trying to extract the TT bar H coupling, it is not only those which are explicitly affecting that Yukawa term, but also the other processes or the processes which involve the production of TT bar, etc. So all those things have to be taken into account. I will give you an explicit example in the next slide. And this is the example that I have at hand. Let's consider the Z Higgs production mode. So within the standard model, we have ZZH production and or gamma ZH. I mean, in principle, this channel is not there, but when you include the effective field, higher dimensional effective operators into it, then this is the standard model contribution, and then these are the bunch of additional contributions that actually you can get from these operators. Like you can get additional contribution to ZZ Higgs coupling, you can get an additional vertex like Z gamma H from these operators. This is a 4-point interaction that can be generated by these operators, like having this. Once again, I mean, you have to just go back and see the nomenclature, what is O1HQ, what is O3HQ, but those will actually generate this kind of 4-point interaction, which is not there in the standard model. And similarly, you can also have additional contribution to QQ bar Z coupling via these effective operators. Okay. So the point is, when you are calculating your ZH production at the LHC, on top of the standard model, if you take the contributions from these higher dimensional effective operators, then all these different diagrams will actually contribute. Whether they will interfere or not depends on their CP nature, etc. But this, all the other graphs one has to actually consider. So for example, O1HQ is this particular operator, which you can check that once you expand them, they will give you a contribution of this sort, including this one. Okay. There is one interesting point that we would like to know, note about this contact interaction, because you remember that in the standard model you have the S channel propagator, but there is no propagator in this one, and this is a contact term. And interestingly, this matrix element, if you calculate, will be independent of S, or no S channel suppression for this EFT diagram. And if you want to write the Feynman rules for this kind of graph, this will show something like this, with this coefficient of C1 HQ by lambda square. And remind you that the standard model contribution, which is this S channel Z mediation, actually has a suppression of 1 by S. So this is the point which Jose was mentioning, that due to the presence of this kind of effective 4-point interactions, which doesn't have a S channel suppression, the cross section actually can grow when you take this contribution into account. And particularly if you go beyond the effective theory limit, this can give you a violation of unitarity. So therefore, it's important that when you take such kind of contributions into your calculation, you must obey the effective field theory limit. What that effective field theory limit is in context of this Higgs production at LHC, we will just talk about that in a moment. So now, if I just measure the cross section and plot the distribution in terms of what is called the invariant mass for the production like Z Higgs. So I'm considering this production like PP going to Z Higgs, and what I'm defining here is a variable called the invariant mass of the final state, which involves the momenta, 4 momentum associated with the Z boson, the 4 momenta associated with the Higgs boson, and the square of it, and when you take the square root, this what gives you the invariant mass of the final state. And this is an observable which you can actually cook up with the final state signals or the number of events that you actually see, subject to the fact that how well you can reconstruct the Z and the Higgs depending on what final state that it is decaying to. But this is an observable that you can in principle see in association with the ZH production. Now, when you plot the event distribution with respect to the ZH, so when I just had the standard model, the distribution was something like this in the blue curve. And when I had the standard model plus the effective operator inclusion, the invariant mass distribution of the signal actually has changed a little, and this is what it is. So there is one interesting point to note first, that the effective operator contribution is actually coming to the higher invariant masses, right? And the reason is once again the one that I just pointed out before, that the 4-point interaction that contributes to this kind of ZH production in the effective operator context is not there in the standard model. In standard model, it's the S channel suppression. So when you include this effective operator contribution, in the tail of this ZH distribution, there is an expectation that this effective operator contribution can show up. I think this is simply because of the fact that we normalize this to 1, the cross sections. This is a normalized distribution that we are plotting. So EFT really shows up in the tail. But the question is whether you can enhance the tail to the extent that you want. The answer is actually no. And that once again comes from that warning that you better obey the effective theory limit when you are actually calculating these cross sections, including the effective operators. And so therefore, there must be a cutoff that says that your lambda must be greater than the invariant mass of the ZH. Now, why invariant mass is the important quantity which defines the effectivity of effective theory that we are taking into account? Because you see that in a sense, because you are producing Z and H, so the 4 momentum added and squared and taken the root is essentially depicting the energy at which this reaction is taking place. So in a sense, the invariant mass is the quantity which depicts what is the energy at which this reaction is taking place. So therefore, once you restrict yourself to this limit that your invariant mass must be less than the lambda, and here we have taken lambda equal to 1 TeV, and that's why you see a cutoff here. This says that you are well and good and you are respecting your effective theory limit. Okay? So this is important while you are doing this kind of searches, and this marks the validity of the EFT regime. I will also give you another example which is about the vector boson fusion production mode. And in the vector boson fusion production mode, so this is the standard model graph that you actually have once again. But when you take the effective operator contribution, the contribution actually come from the modification of the Higgs gauge boson coupling via the same operators which we just talked about. You can have the effective operator contribution affecting your, this particular vertex like Q, jet and the gauge boson, as well as you can have an additional contribution of Higgs coming out from this particular graph. So there is nothing to worry if you do not see it from this nomenclature right now. It's just that you have to take that operator, take that unitary gauge expression for the phi, expand the operator, see where exactly the vertices are contributing, and you will be able to see that there are additional contribution to this vertex, or there is a new vertex which you are finding through these channels. And once again, this operator comes into the play like H dagger H W mu nu tilde W mu nu here, which you remember we sort of said that this is one of the CP violating operators. So there is a CP violating operator that is contributing to this particular channel. So now the question is there a way that we can probe the CP violation? And what we can do, so this is the reaction, say let's for example, we are taking this graph and you remember that this is the vertex where the contribution is coming from that CP violating operator using the field strengthener and its dual. And so these are the 4 momenta associated with this thing, and then you define the kinematic variables like the transverse momentum of the final states of the jets and the Higgses, etc. And this is an interesting variable that we define, which is the phi, which is tan inverse of Py by Px. Now the question is, can we construct a CP odd observable in this process? Now the CP odd observable can be epsilon mu nu rho sigma k mu k prime nu q rho q prime sigma. Now what exactly is this thing? If you expand this, it can be written in terms of 2e prime q prime cross q dot k, where all these are the momenta associated with the initial and final states. Once again, this is a pattern level thing that we are saying. In order to reconstruct this momenta in context of a collider, one requires to do a bit of hard work. And it is not very difficult to check that this relation comes from this construction using this triple product of vectors A cross B dot C is equal to epsilon ijk ai bj ck. And if you do a couple of steps of this calculation, then you can show that this quantity actually transmits into something like 2 prime qt prime sine of delta phi jj, where delta phi jj is nothing but the separation of the angle of these two jets which are coming out. And so therefore, this observably, if you construct, carries the imprint of CP violating Lorentz structure that is contributing to this kind of a production. So this is an interesting direction that one can also look up. And if I plot the delta phi jj distribution once more with normalized events, my apologies to Anupam, and then once again we see that this blue line is the actually one which has the standard model contribution, whereas the one in the red is the one which has this additional contribution of this CP violating operator. So therefore, there are ways of distinguishing, or rather seeing the effect of these different higher dimensional operators contributing to your different production modes associated with the Higgs, and infer whether they whether they can, I mean, what you do now, that because we have no excess in any of these channels beyond the standard model, what people usually do, that they put limits on this Wilson coefficient by the lambda square. But we all know that LHC is going to be operational for higher luminosities, and where we will have many more data, much more data, and there is a possibility that these effects, however small they are, can actually show up. So there is a possibility of distinction between just the pure standard model and standard model plus effective operator contributing to this kind of productions.
In this one, basically, there is a initial first gradually down, that is one.
This one, right? Yeah. No, this is the specific thing, that because we had the CP violating operator contributing here, that shows up in terms of this delta phi jj, and there is a contribution which is coming up from this 2e, the transverse momentum, etc., and whatever that was sine of delta. I forgot the formula. Let me go back. Yeah, sine of delta phi jj. So this is specifically due to this particular way that the contribution of the CP violating operator is, I mean, so the separation angle between the jets can be a good observable to distinguish between the standard model and standard model plus effective operator contribution via the CP violating contribution.
In case of the standard model, there is not this kind of
This will be falling, yeah. So the maximum is actually when phi jj is equal to 0, right? I mean, a delta phi jj is equal to 0. That is, they are actually collinear, and then as you separate the angle more, the contribution drops. But here, for this particular case, there is a peak, yeah, with this inclusion of the CP violating operators.
So in your earlier example, so you consider contribution from the phi q operator in that Z production, right?
This one, example one, right? Yeah.
Wilson coefficient, the same operator.
Yeah.
So can also get constraint from B physics.
Absolutely.
So
Yeah.
whether So that will affect this.
Of course. I mean, see, here what you are saying that you have chosen a scale lambda, but this Wilson coefficient that you have chosen here is usually order 1, that's what we are saying. But whether that is consistent, if this operator contributes to other flavor observables or other low energy phenomena, that has to be taken into account. So when you choose your C by lambda square together, it is to make your calculation consistent, you have to see whether there are other contributions that this operator can contribute to. Say for example, you are saying that if it is contributing to some flavor violation or something, that has to be corroborated, and depending on how large or how small that C is, will definitely alter the visibility or the distinguishability of the contribution of the effective operator, for sure. I mean, if you blindly take C equal to 1, which we are taking here just to show as an example, but in a careful analysis, you have to take into account those kind of other constants, and that will definitely say how large the feature will remain the same, the pattern of the plot remain the same, but whether it is inflated or it will be subdued depends on how large this Wilson coefficient is.
Thanks.
Yeah. Okay. More questions? Okay, let me get back to my last slide. Yeah, so the last point that I had to say is, remember that this distribution that I have showed is only signal distribution, and signal distribution coming from the standard model, and the signal distribution coming from the standard model plus effective operator. But life is not that simple. There are huge standard model background contamination which is going to affect your observable. Like say for example, you take TT bar contribution, that will contribute to, suppose you take ZH production, Z going to L plus L minus, Higgs going to B bar. There are many processes which has nothing to do with the ZH production, but will produce 2 leptons of opposite sign, 2 B jets in the final state. If you have to, if you want to do a realistic analysis, you have to take all those contributions seriously. And if you take all those contributions seriously, the first question that rises is the distinguishability of the signal itself. The distinguishability of the signal and the distinguishability of the signal coming from the standard model plus between standard model and standard model plus effective operators comes next. The establishment of the signal over the background fluctuation is the first important point, and there it is not very easy. So all these nice features that we just talked about is subject to the signal discovery over the background contaminations, and this is where there are these recent machineries which are being used to segregate the signal and background distributions via this machine learnings and deep learning techniques, which many of you I am sure are working upon, and so this is going to be a great help, so therefore for a realistic analysis we have to take everything together, the signal plus effective operator plus standard model background. Do choose event distributions or event variables or final state variables that discriminates your signal and background to the best extent. Use those to fit into the machine learning tool that you are using, and they will choose a combination of those variables which actually segregates the signal and background best. I mean, just you have to know how to do that, and once you do that, then you ask the question, can I now distinguish between the pure standard model contribution and the standard model plus effective operator contribution? So this is the procedure by which a realistic calculation proceeds. I think we have also a talk by Shankho, so who is going to talk about more on the Higgs physics and its searches, including the effective operators in context of LHC and in particularly with higher luminosities. So stay tuned for that, and I will finish here. So we are finishing early, that's not a crime. I think we have a photograph session also. So yeah, okay, thank you so much. More questions if you have. Tisha. Someone should give her a microphone. Sorry. She is an expert, yeah.
I am asking that in the background there can be contamination from other EFT operators
Absolutely. Yeah, that shows that she is a practitioner. So, yeah, you are absolutely right that it's not only the effective operator contributions to the signal, but when you take your effective operator series as a base for your signal, then you also have to take that into account for the background searches also. You are absolutely right. Yeah.
So in that case, studying just one observable is not sufficient, right? So we need to take more observables into account to distinguish between the EFT operators also.
Absolutely, precisely. Yeah. So one observable will not be. So we are not talking about those how you can extract or put limits on the Wilson coefficients because that would be a little complicated, at least for this lecture, I thought. And also I was not prepared. So that's the second point. But you are absolutely right that when you are putting bounds on your Wilson coefficients divided by lambda square, because you in principle can't segregate between these two at this moment, then you have to, it's better that you take like, you know, vector boson fusion, Higgs-Stralholm, put together, and then you will be able to see the distinction, or rather put a consistent bound on those kind of, because they will contaminate all those signals that you are seeing. So it's better that you do not choose one particular production mode and a particular signal mode, rather you look for all those different cases and put the bound together from all these different observations. Yeah, absolutely.
Can you go on the slide where minimum mass for G Higgs?
Correct.
Okay, so here in the tail, so the red plot, it is for EFT, right? So it is for 1 by lambda square contribution. That means 6-dimensional operator is contributing significantly, right?
Yes, yes.
Okay. So when we write
subject to the C value, which someone asked, that what is the C value? We are taking C equal to 1 just to show you a nice distinction, but in reality, if you have to take contributions from other observables, which restricts your C by lambda square, then if you take a smaller value of C, it will not be this prominent. Yeah.
So here in amplitude square, we will have 1 by lambda square into standard model interference.
Absolutely.
Then we will have 1 by lambda 4 in a
correct
quadratic. Okay. Then we should have contribution in principle from 8-dimensional operators.
Absolutely. So in cases, this is a very important point that you raised, particularly for those operators, those in particular which is CP odd, they do not interfere with the standard model. So if you are taking the CP odd observables, because it will be perhaps helpful if I just write one line. So in a sense, you are saying that this is MSM plus MEFT, which is like supposedly whole square, and so therefore MSM square plus lambda square plus, right. So there are cases, I mean, whenever this interference term is present, depending on how large your contribution or contamination is, you have to decide whether you take also the contribution from dimension 8 operators. But if it is not there, then perhaps it is imperative that you have to take those higher order corrections. Yeah. Well, in that case also, I mean, this has a caveat, because if you take the dimension 8 operators which are CP violating at the same time, they will also not interfere, and they will come even at the 1 by lambda to the power 8 order actually. So, but yeah, in general your comment is right, that depending on how large this contribution is, you can decide upon whether to include this or not.
So by this plot, it seems that the quadratic is contributing more than the interference.
This is, yeah, you are in a sense right, because this is mostly coming from this graph. I mean,
yes.
whatever. Yeah, you are right. You are right. Yeah. So, yeah, you are right. Yeah, that is because we are just taking this C to be simply order 1 and lambda equal to 1 TV to show the case. Yeah, you are right. So, this contribution is predominant in this particular case. Yeah, true. I mean, the distinction in the tail that you are showing.
So, in that sense, dimension 8 operators are also important.
Are it's blindly neglecting that will be difficult. Yeah, true, true. Yeah, life is complicated.
Okay, one more, the delta phi distribution.
Yeah, yeah.
So in PP collider, we cannot make genuine CP out observables like we do in lepton colliders, right?
True.
Because we have PP means composite PP
Particles, yeah.
So we cannot do that. But is there any way, like you have shown in the
previous slide, that the separation between the
just by kinematic structure of the operators.
Yeah.
So is it hard to do always? Means always we cannot do that,
right? So your question is how legitimate?
We cannot construct always
a CP violating observable.
Yeah, just by looking at.
True. So in principle, the argument for the previous slide was the following, that see, ultimately these are measurables, like energy of E and E prime are essentially this K and K prime, the initial, well, I mean, so, and this transverse momentum associated with the jets, these this can be sort of measurable. So that's what we argued, that then perhaps this delta phi jj will have the seed of the CP violation contribution to this kind of to this production. But you are right. I mean,
although this is sign sensitive, means if you flip J1 by J2, but we cannot do that in diazide production in LHC.
True. True. Yeah, it's a very naive calculation. I mean, it ignores or undermines several important observable possibilities or consequences, as you are pointing out. True. Yeah, agreed.
So can we understand? Can you go on the delta phi distribution?
Yeah.
So in PP collider, the jets are very important, right?
Mm-hmm.
So they are like back to back.
Absolutely.
So that's why in standard model delta phi is around 0.
Absolutely.
Or if you look at if your delta phi goes from minus pi to plus pi, then it will be like symmetrically peaking at 0, so peaking at minus pi and peaking at plus pi.
True. This kind of a distribution. Yes.
And there will be no events around delta phi.
Exactly.
It is here because it is
more. Yeah, there is a delta phi jj contribution.
Okay, yeah. Then so somehow if you look at delta phi jj equal to pi by 2, that means somehow beyond standard model physics is pushing one of the jets or angle between the jets around pi by 2.
True. Absolutely.
Yeah, that we can understand from that structure which has PT.
Exactly.
Right. So once you have delta phi around pi by 2, you will have
large contribution coming from essentially sine 90 degree equal to 1. The sine, yeah, absolutely. Yeah, that's very nicely elaborated. Thank you. Yeah, that's very nicely explained. So what he is saying, that just the contribution, if you look into, which is actually sine of delta phi jj, so that will give you a peak at delta phi jj equal to 90 degree. So that's what it is showing. That. Yeah. Any more question? Shogun.
Yeah. So in this red line, so is there only this CP odd effective operator is considered?
Yes.
But there might be, I mean, other CP even operators in that dimension.
Absolutely.
So if we consider that, how this?
Yeah. Well, the answer is I don't know, because we have not done the calculation. So, or rather, we can do the calculation. I mean, it's not very difficult, but this feature will be there. So, this is the distinguishability that we wanted to show due to the inclusion of CP odd operators.
So, those CP even operators that won't be depending on this delta phi JJ?
That will not give a distinguishability in this regard. So, you know, you will inflate the structure, or, you know, depending on what are the other combinations that you choose, you may not retain this beautiful structure as we have here. Yeah.
Thank
you. Yeah. More questions?
Yeah. So in the standard model, we don't have direct coupling of Higgs and gluons.
Yes.
But here in the effective field theory, there is I saw a vertex that Higgs
you
to
can. G mu nu A, G mu nu A.
Then what will be the structure of the coupling constant? Because in the standard model, it's a loop induced thing, and here you are writing the.
Jose is going to do that for you, not in general for the gluon, but he is going to argue that there are a class of operators which cannot be generated at the tree level, and those are what are called loop generated operators. And when you include the field strength tensors in particular, like that you pointed out, that can be shown that that can only be generated at one loop. Now, what new physics that can generate that requires a bit of, you know, you have to look into that, but the G mu nu H dagger H operator is certainly one of those new, some of those what is called the loop generated operators, and which will have an additional suppression of 1 by 16 pi square. So, in principle, if you take the coefficients, Wilson coefficients having the same order as those of other operators which can be generated at tree level, which he will mention as a potential tree generated operators, then the calculations are not completely all right. So, this is something, because then it will be saying that you are taking the Wilson coefficients 100 orders more, that if you take the C of the order of 1 for loop generated operators, because it has an inherent 1 by 16 pi square sitting downstairs, then you are basically inflating it too much, and that goes beyond the weakly coupled new physics system that we are generically talking about. So, there are bit of caveats. So, you are absolutely right that these operators cannot be generated at the tree level, and this will only come at the loop level. Okay, if no more questions are there, then we can finish this session, and I think we have a photograph session right now. Okay.